Alright, hello. Testing. Alright, hi everyone. Welcome to the stream. Sorry I'm late. So on this stream we are making a rendering engine in Vulkan using Haskell. And last time, let's pull up our examples. Last time we got square rendering to the screen using vertex buffers. And today, we're gonna try and get something rendered to the screen using uniform buffers. The first thing we're gonna look at is memory allocation with the Vulkan memory allocator, and then we'll move on to looking at uniform buffers and things like that. So I haven't had as much time to prepare for this stream as I would have liked, so we'll see how it goes. Might not be as straightforward as other streams. So, to start us off, I'm gonna open up a new module and call it allocator. So the problem that we are going to face is with our previous example of the buffer, the vertex buffers, we're going to want to update, we're going to want to create a buffer for the uniforms, and we're going to want to update that every frame. And so the sort of memory, sort of allocation strategy that we had for our vertices was to create, basically create our buffer once and just reuse that. But because we're going to be updating a buffer over and over again, I thought it might be nice to allocate some memory that is kind of like, hopefully, if possible, device local, so on the GPU, but visible from the CPU. So it's something that we can update every frame quickly. And doing that using like my own memory allocation strategy is like not on the top of my to-do list. So we'll try and use the Vulkan memory allocator, which is something produced by AMD, GPU Open. It's just like a Vulkan memory allocation library. It's easy to use, it's got decent documentation, and like it allows us to get as fine-grained and granular as we like, or as high level as we like. So we should open up documentation and get started. So I'm just gonna put this all in a different module because like I'm not sure how complicated this is gonna get. So um, let's import Vulkan. What is it? All right, Vulkan memory allocator. That's okay. We'll import the Vulkan memory allocator. We'll create our own type. That's just an alias at the moment. Might get more complicated later. And let's create a function create that, or how about with allocator? All right. So, to create one of these things, we just have to use VMA create allocator and pass in a create info structure. And what does that look like? All right, so we have a few things. VMA allocator create info. Blah, blah, blah. All right. So we're going to need to pass in the physical device from our context, the logical device from our context. What are these flags? Let's have a look. All right, we won't be using any of those flags, so we can just put VK0. Okay, just pass in our physical device and our device. The preferred large heap block size, we can just leave as nothing. The default is 256. 56. Megabytes, which is more than enough for us. Allocation callbacks, we can just leave that as nothing. Device memory callbacks, we'll also leave as nothing. The heap size limit. Pointed to device size. Pointed to an array of limits on the maximum number of bytes that can be allocated out of a particular memory heap. We will just leave that as null pointer. We're not going to be using that. Vulkan functions, we can leave that as nothing for now. We're also going to need the instance. We'll get that from the Vulkan context, and this is a handle to the instance. So we will call instance handle on the instance. Let's pass in the API version as a parameter. And what's this last one? Pointed to an array of external memory handle types for each Vulkan memory type. We'll just leave that as null pointer. So we're almost definitely going to need to import some things. VK0. Ah, this has to be 0 rather than nothing. Okay, VK instance handle. Where do we get that from? VK instance handle. Oh. Hmm. Hmm. I'll get back to that. If we go to instance, Vulkan instance. Yeah, it's there. All right. So we'll have to import a particular module to get access to that function. Cool, that looks like a start. All right. Let's give this a type signature. Nope. And let's change these. We'll pass in just the device and we'll get the handle. Alright, device. So, BK physical device handle and BK device handle. Alright. Cool. And then destroy will just be VMA destroy allocator. And that. Yep, that just takes one parameter, which is the allocator itself. Then we'll write a function called withAllocator that just pairs the create and destroy calls together. So same parameters, physical device, device, instance, Vulkan API version, resource.allocate, create, physical device, device, instance, Vulkan API version, and then we'll destroy that. Import our resource type. Fix some typos. Alright. There we go. So we've got something to create and destroy an allocator. So let's just try and use this. See if we can get anywhere. So in our buffer example, just find somewhere and we'll create our allocator. VK instance and the Vulkan API version, which we'll get from here, config application info. Right, API version. So I just got an error about API version being ambiguous. So a lot of like we can have a look at this. Yep. So we have a look at this module and we look for the words API version. Can find it on physical device properties. We can find it in this application info structure and probably somewhere else too. Nope, okay, there's just those two places. So Haskell can't tell the difference between the two, like it's not able to by default infer like um, which API version we want to use. So I found that the easiest way to fix this is to turn on overloaded record dot, and that gives us the ability to do this. Cool. So we can kind of use the dot syntax that like it's familiar from lots of different languages to drill into that structure. Now we have to import our allocator. And that's it. We're not using it, but we have tried to initialize it and it will get destroyed at the end of our program. So if we load, load our example, try it again. Oh, we crash. So what's going on here? Assertion get instance proc address and get device proc address failed. To use VMA dynamic Vulkan functions in a new version of VMA, you now have to pass these things as Vulkan functions. Okay, let's have a look at the documentation. This one. So, you may need to configure importing Vulkan functions. There are 3 ways to do this. If you link with a static library, you don't need to do anything. Alright. We might be that. If you want to fetch VMA, if you want VMA to fetch pointers, you got to set VMA dynamic Vulkan functions to 1, and then provide pointers to these 2 functions. Alright, so let's go to package VulkanMemoryAllocator. This is the Haskell package that we're using. If we go to the GitHub page for that package and we search for that string, this string. Static. Okay. So it looks like they are defining static Vulkan functions to 0, which means that we must be on that dynamic path. So it looks like we'll have to provide pointers to the vk get instance proc address and the vk get device proc address functions. And that is this parameter. Okay. So jump over to our allocator. We are going to create a Vulkan functions piece of data. We'll start off with its default using vk0, and we'll set the get instance proc address function to something and the get device proc address to something else, and then we'll pass these Vulkan functions in. Just Vulkan funcs. Alright, so where are we going to get those from? So if we go have a look at the instance, for example, it's got this instance commands, and we're looking for get instance proc address. Alright. Okay, so we should be able to take our instance, go instance commands, and then Vulkan dynamic, vk dynamic dot p vk get instance proc address. So we'll import Vulkan dynamic as vk dynamic, and we should be able to do something similar for get device proc address device commands. Alright, let's figure out what's going here. Oh, yep. Let's use overloaded record dots. Okay, couldn't match type this to IO. Oh, we're probably just going to have to cast this pointer to the right type. So, cast from pointer. Import that. Do the same thing here. So that's just going to cast the function pointer from one type to another. It is the right type. Well, it's not the right type, but it is the right function. So it should be good. All right, let's reload our example. And run that. Oh, and we didn't crash this time. Still looks good. Okay. So so we've created our allocator, but now I want to create an allocation for our uniform buffer. And I want this memory to, if possible, be like writable, directly writable from the CPU and like directly readable from the GPU. So Vulkan Memory Allocator has this recommended uses patterns document, and it talks about like GPU only resources, which we'll get to later, staging copy, read back, and then there's this kind of advanced data uploading. So it says for resources that you frequently write on CPU via mapped pointer and frequently read on GPU, e.g. like a uniform buffer, it lists some options and it says, thankfully we take care of that for you, and this is how you do it. So you set some flags, the Vulkan Memory Allocator will try and allocate that memory for you. If that's worked and like it's both host visible and GPU visible, like host writable and device readable, then you can just go ahead and use the pointer. And if it's not, then you have to kind of do what we were doing before with the vertex buffers, which was you have to create a staging buffer and a device buffer and like upload the staging buffer to the device buffer. But right now, we'll just assume that it always works and that we get our just mapped pointer, and we'll go ahead and fix that later. So I'm going to write a function called with uniform buffer. given an allocator and a size, and we'll just copy a link to that documentation so that we can refer back to it later. All right, so we have to make a buffer create info, and that's pretty straightforward. We've done that before for the vertices, and all we need to change really is we need to change this to uniform buffer bit, and the Vulkan memory allocator documentation says that we should use this buffer usage transfer destination bit. So that's the Vulkan buffer create info. Now we need to create some allocation create info for the Vulkan memory allocator. So, just referring to the document, we got some flags. Those flags are allocation create host access sequential write bit, vma.allocation create host access allow transfer instead bit, and vma allocation create mapped bit. So those are the flags that we'll be using. We'll just say memory usage auto, which lets the memory allocator choose that for us, which is usually the recommended setting. These are required flags. These are preferred flags. We're going to accept any memory types that meet the requirements. We don't have a pool to allocate from, or we don't have a custom one, so we'll just let the Vulkan memory allocator handle that. We're not going to associate any user data with this allocation, and we'll just set the priority to 0 because we're not using priority. Then we will resource to allocate. So vma.create buffer. So we're going to create a buffer using the Vulkan memory allocator. What have we got here? Allocator buffer create info. Yeah, cool. So we're just going to pass in the allocator, the buffer create info, and alloc create info. That's going to give us a buffer, an allocation, and some allocation info. And later on, we're going to destroy that buffer. That allocation. Alright, so this is a resource, and if we were to get this resource, we would get like a triplet of buffer, the allocation, and the allocation info. And what I want to do is I want to print some information. I don't really care about the buffer itself right now. I just want to print some information about the allocation. So we'll get some information about the memory type that was chosen. So memory prop flags. And what we're going to do is check if that memory is host visible. Because what that means is that we can write to it directly, and that means it's like one of those memory types that's device readable and host writable. which is like perfect. So basically, I'm just trying to confirm that we're getting the type of memory that we're expecting. Because yeah, the other option is that Vulkan could the Vulkan memory allocator decide like, oh, there's actually none of that kind of memory, so I'll allocate some device local memory for you that isn't host visible, and it's up to you to figure that out, and then transfer the data over in a staging buffer, which is what we do for the vertex buffers. But we're just going to assume that it's able to allocate some memory for us, which will probably be true of most dedicated GPUs. Um, so we should be good. Let's give this a type signature. 164 for the size. Cool. All right, let's allocate this in our buffer example and uh, just see what prints out. Let's make it 256 bytes big, and we'll just ignore the result. Cool. So it's returned to us like a memory type, some pointers, offset, it's the correct size. We've got a pointer to like the buffer itself that we can write to. It's no name. Cool. It's printing the memory property flag bits, which isn't really going to mean anything to us right now. But the most important thing is that this is printing true. And what this is doing is just checking that the host visible bit is set. So we've got the type of memory that we want. Now, we do something a little bit more interesting, and we allocate this uniform buffer every frame. So this is how I imagine we're going to use it, is we're going to allocate a little bit of data every frame and upload our uniform buffer information to it, and then we'll draw with that. And what I want is because this is happening every frame, I don't really want to be doing an actual allocation every frame. And I'm hoping that the Vulkan memory allocator will just like allocate a big block of memory and then give us a subset of that memory, little sub allocation. And when this frame finishes, it'll release that resource and then give us, start again and not create a large amount of memory and not do any allocations really. Just sub allocate from a bigger one. So let's have a look what happens. All right. So you can see that over time the offset is increasing and the pointer for the map data is changing, which suggests to me that we're not freeing the data. Which is true, because what we can see here is that with the next frame in flight, it's, if we hover over here, it's taking like a resource T in this case. So any resources that are created in the lifetime of this block here aren't freed when we go to the next frame, which is not what I expected, and not what should be happening. Oh, hello, tech support. What's OMG? So, well, thanks for the follow. It's great to have you. I will caution you, I'm a little bit tired today, so we're a little bit uh, running on steam, but thanks for the follow. Feel free to ask any questions. I'm happy to like jump off topic and talk about anything really. So yeah, we're making a rendering engine in Haskell. And what we found here is just that we're not freeing resources between frames because we're not running our resource T, so it's not limiting the scope of our resources to the frame. It's just going the scope of those resources is just going to increase and increase and increase. So the simple fix is just to run that resource T, and then anything that's created in this block will stay within this block. So what I'm hoping now is that when I run this code, the offset of the allocation info is the offset of the allocation is not going to increase. It's going to be the same, and the pointer is going to be the same. And that would be showing that we are freeing the data, and it's just allocating to us the same block. Cool. Yep. So now you can see that the offset of the allocation is not changing. It's always 0. And the maps data pointer is always the same. So that's good. And the idea here is that we'll have this fast allocator that can allocate some memory for us every frame. It's not actually doing any allocations. It's just allocating one big block for us, managing that and sub-allocating within it. And then we'll get back like the buffer and a pointer, and then we can just poke some data into the pointer. So let's go back to our allocator. So get rid of this printing now. Oh, gone ahead and frozen my editor. What did I do? I swear, Haskell language server just really doesn't like underscores. Alright. So a little to do we should write here is that we want to handle non-host visible memory. Because like I said, the Vulkan memory allocator might not be able to allocate to us host visible and device local memory. But in most cases, with a dedicated GPU, it's going to be able to, so we're just going to ignore that. All right. So we're going to return a tuple of our buffer. Oh, actually, that's not going to work. Tuple of our buffer, and we're going to need to find our pointer into that memory. So not in allocation, allocation info, map data. There we go. So we should just return allocation info dot mapped data. What's going on here? Oh, yep. PK buffer. Okay, so we're going to return to the buffer and a pointer to that buffer. And we're going to wrap it in a resource like we do everything else. Well, everything with a lifetime. Vulkan. So, yeah, chat said that Haskell is the easier thing to wrap the head around here than Vulkan. Yes, Vulkan is very testing. It's, yeah, ugh, rough. And the only reason that I'm really able to do this is because I've tried and failed a couple of times before this, like doing like making this rendering stuff. And I'll like go and I'll make some like abstract thing and I'll try and like handle them Vulkan stuff. But it's just, every time you do that, I just realize, oh, I actually didn't understand this part of Vulkan and gone and made a mess of things. But now hopefully I understand like just enough. So got our allocation. So we're just going to work in our resource monad here so that we can group this buffer and pointer with the original resource. So that should be good. Yeah, please do. And keep me up to date. Tell me what you discover. Because, like, it's so unlikely I'm going to get this right the first time. But, we'll see how we go. I'm really interested in, like, yes, absolutely. I think Haskell would be good to write 2D games in. I haven't heard of Dragon Ruby. Oh, cool. Okay, so it's like a game development toolkit. Oh, Ryan C. Gordon, I've heard of that guy. And cross-platform too. Yeah, so one of the things that like been working on is compiling Haskell, like cross-compiling Haskell. Oh, live reload, that's so good. I feel like that's something that's a little bit far away with Haskell stuff. Um, yeah, what time travel. There's this paper about like functional reactive programming, and I think that would be really interesting to give to try. Like they have some papers here where they mention making games in using this sorts of thing, and I was very interested. But I won't jump into that. But yeah, I'm hoping at some point I can kind of make the renderer like able to be used by like one of these functional reactive things. Um, it seemed pretty simple, but we'll see. Yep, can relate. I haven't tried a camel. Okay, cool. So we've made our allocator, at least for uniform buffers, with some simplifying assumptions that we'll get back to later. All right, let's commit this. Uh, we're not actually going to use the allocator in this example, so we can get rid of it. And what should we call this one? Just say use Vulkan memory allocator. Cool. So I should have mentioned this at the start of the stream, but you can follow these commits live at github.com/sambnt/rort or rort. Um, yep, so on the master branch, you'll see our commits. So you can follow along with them and all the previous ones. And I also upload these streams to youtube.com/@SamBennett or BNT underscore TV. Do I think Idris might be nicer for this, and do I find the lazy aspect of Haskell standing in the way? Um, no, I think the lazy aspect of Haskell might be actually really nice at some point. At this point, I haven't taken advantage of laziness in any like particular way, but I think it'll be interesting in the future. Like as we work more on this project. Uh, and I'm so used to Haskell's laziness now that it's just fine, good. Um, yeah, I haven't really looked at Idris. I mean, I have looked at Idris and I really want to use it more, but I haven't given it a serious go. And for like this stuff, like what I'm really like, I think the problem with maybe Idris is just the practical one of just like with Haskell, I've got a Vulkan library with all the bindings, and then I've got a VulkanMemoryAllocator library with all the bindings. So library support might be more of an issue. Um, but theoretically, it might be nicer, especially like linear types and linear resources. Like basically all the code here is resource management. Like, so more interesting ways of doing resource management would definitely be appealing. All right, what are we gonna do next? Oh, so one thing we did with the buffer example that I forgot to commit was we limited the scope of the resource created in the frame to the frame. And we'll just do the same for the triangle example as well. Great. Commit that. Lifetime to scope of frame. I should probably note this only works because we wait for the render to finish before leaving block. So what might be a problem is if you free the resources before the frame has finished rendering, um, because like, for example, we create the command buffer in that frame. Okay, this is the frame scope. We create command buffers. If you record to those command buffers and then submit them, and then don't wait for the render to finish, this block will exit and the resource will get destroyed, so the command buffer will get destroyed, and then the GPU will be like real confused because it'll be like, oh, I'm trying to render this, but it doesn't exist anymore, and you're gonna have problems. So the only reason that this simple fix works of running the resource T is that at the end of this, we present our image and that waits for the semaphore render finished, which means that the rendering has finished. Um, so yeah, that's the only reason it works, which is fine. It's likely that this is going to be true um, even as we develop this renderer out. So one thing to say is that the way we're developing this renderer is we're just like as much as possible just using the raw Vulkan calls, maybe with a little bit of wrapping. We have a little bit of wrapping around resource handling, but we're just going to use raw Vulkan calls. When things get unwieldy or annoying or repeating a lot of code between examples, then we'll start to like extract those bits out. So we're not going to aim for like abstraction yet. We're just going to like iterate. So push that up. And then I think we should start on our uniform example. Right. So we'll create a new example called uniform. And all we're going to try and do here is take our buffer example, which renders a triangle, sorry, a square, and we want it to render a square in perspective. It's a simple one, but getting there is going to be interesting. Okay, so like I said, I did do some research on this project a number of months ago, and so I sometimes do have an example to refer to. Right. So in our buffer example, which is now going to be our uniform example, we create a window. We initialize the Vulkan context, then we start loading shaders. Let's change this shader to uniform buffer. So our uniform buffer shader is going to be just like our vertex buffer shader. Thanks, man. I really appreciate it. Thanks for the follow and good luck with work. Okay, so our uniform buffer shader is just like our vertex buffer shader, except we're going to take in a binding, or we're going to accept a binding, like a uniform binding, and then we're going to use that to multiply our position by the matrices that we find on that binding. So this is a pretty typical model view projection matrix. Cool. So let's compile that to SPIR-V. So GLSC, I'm going to output SPIR-V from that. And now we've got our new vertex shader loaded. Cool, so we don't need to change anything about the swap chain initialization. Excuse me. Don't need to change anything about the shader stages. We've still only got 2 shaders. But now we do need to change something here. We need to change our descriptor sets. So let's refer to a previous example and find our pipeline layout. Okay, so we're going to need to create a set layout. So that's a descriptor set layout, and specify it when we create the pipeline. With VK set layout, it's going to take in the device. We're going to have to write this function. For now, we can just pretend it exists. Descriptor set layout create info. And what is this structure made of? Okay, so we've just got our bindings in here. So we've got one binding. We have a look at our shader. The binding number is 0. So let's specify that here. The type is a uniform buffer. So it's not like a image attachment. we've got one of them, and it's bound to the vertex shader stage. This last parameter is for immutable samplers, which I'm not even sure what they are, so we can just leave that as empty. I know what a sampler is, I don't know what an immutable sampler is. Cool. That's our set layout. Let's create this function and put it where we keep all of our other resource management functions. So this function is going to take a logical device and a descriptor set layout create info structure. And then it's going to return to us a resource of a descriptor set layout. So this is just telling us about the structure of the bindings in our shader. This is where we tell Vulkan about that. So. Device, create info. Same pattern as we do with all of our resources. I'm going to give it a way to create the resource. So create descriptor set layout, device, create info, nothing for the allocator callbacks. Maybe we can integrate VulkanMemoryAllocator in later. Not really sure how that works. From what I understand, like the VulkanMemoryAllocator is just used for like buffers and images and things like that. Not for other resources, but I could be very wrong. But for now, we'll leave it as nothing. Great. There is our descriptor set layout. So let's add this example. It's already added. And let's make sure that we can compile this example. Okay. Type applications. And we need to add this import. And make sure to get our resource. Okay. So that's our set layout. And then our pipeline layout. Now we need to actually create a descriptor set. So that was the layout of the set. Now we actually need to create the descriptor set. And to do that, we're going to need to create a descriptor pool from which we can allocate the descriptor set from. And then in the frame, we're going to write our data to the uniform buffer and then bind that buffer to that descriptor set. And then we can draw. So that's the kind of like steps that we'll be taking. It's been just over an hour, so I'm going to take a little break and then we'll get back and work on that. How do I zoom in? No. All right, cool. I'll be right back. Thanks, everyone. And we're back. Okay, so yes, we created our set layout. We told Vulkan about what uniforms, what descriptor sets, rather, we were going to be using. Now we need to actually go ahead and create those descriptor sets. And the first thing we need to do is create a pool to allocate the descriptor sets from. And that would look something like, we've got a command pool, so it's a similar sort of idea. Let's go ahead and create a descriptor pool. With VK descriptor pool, let's have a look at what the type signature for that looks like. So device, descriptor pool, create info, and allocator. So VK descriptor pool, create info. And then let's have a look at what this structure is. Won't be using any of those flags. Can always give a unit as the next element in the chain. Like I said, VK0 for flags. And the pool, max sets. So we've only got one descriptor set. But if you had multiple, like this would be the number of descriptor sets that you want, the maximum number of descriptor sets that you want to be able to allocate. So like descriptor sets, like often like you might use a frequency based model where you have, say, like 3 descriptor sets. You have one descriptor set that changes not very often, and that would be like global, like camera position, for example. You have a descriptor set that changes a little bit more often, and that might be like materials, and then you have like a descriptor set that's changing like all the time, and that might be like a model's position. And so like in that case, you had 3, you want your max sets to be 3. Something to be aware of though is that we actually can't use descriptor pools from multiple threads. They're not like thread safe to use. You have to allocate a descriptor pool for each thread. And they have to exist for as long as the frame is being rendered to. So we'll get to that later, but we can just assume now that we're just going to use one, only have one thread. All right, max sets and then pool sizes. So vector from list, and then we'll specify our pool sizes. So descriptor pool size is made up of a type and a count. So VK descriptor pool size. What types do we have available? Descriptor type uniform buffer. There it is. And we've just got one of those. Our descriptor set is made up of one uniform buffer. All right, let's write this resource function. Like in the same place we have all of our other resource functions. VK device, VK descriptor pool, create info. At the end, we're going to get ourselves a descriptor pool. All right, device, create info. Same as always, allocate will tell it how to create the descriptor pool. and nothing for the callback, and then how to destroy the descriptor pool. Let's just look that up. Device descriptor pool. And the allocators. Okay. We'll import that. So now we've got a descriptor pool. So, alright, now we need to allocate our descriptor set from the pool. So, we'll write a function for that with vk descriptor set. A descriptor set allocate info. And what we're going to use is allocate descriptor sets. So we'll look that up. That's going to return to us a vector of descriptor sets. We'll just convert that to a list because it's a lot more convenient for us. So device alloc info equals resource. I'm going to convert whatever comes out to a list. Resource.allocate VK allocate descriptor sets. So device alloc info, that's it. Then we've got 3 descriptor sets. So that's 3 descriptor sets, device, and descriptor pool, which we can get out of the allocation info. Okay, that should be good. Just make sure that compiles. Looks good. All right. So I guess just after we create the pool, we can allocate the descriptor set. Because, like I said, we're only going to be working from one thread, only showing one frame at a time, or rendering to one frame at a time. So we'll get away with that. Because typically you create like a descriptor set for each frame so that they can update independently of each other. But we're not going to worry about that right now. So we call this function with vk descriptor set. Going to give it the device, then the descriptor set allocate info structure. Go have a look at that. So we've got the chain argument, the pool, and the set layouts. Okay. Well, the chain argument is always unit. The pool, we're just going to get that. And then the set layouts, we've just got one of them. Cool. Those are our sets. We've only got one set, so let's just get that. What have I done wrong here? Ah, cool. So we've got a single descriptor set. So all I did there was just take the first element out of the list because I know that I'm only allocating one descriptor set. Cool. So each frame, we're going to use our allocator. So let's find our frame. Here we go. So we'll, it doesn't really matter where we do it. Let's do it here. Let's uniform buffer size equal. So we're going to upload 3 4x4 matrices. So that's going to be 3 times the size of undefined M44 float. So this is just like a, you might not have seen this before, size of the type signature for it is, it takes any A and it's going to return an int. But instead of, it doesn't actually use that value. So instead of passing a value, you can just pass undefined and give it the correct type, and it will give you the correct size. So that's the size of our uniform buffer. Then we're going to get the uniform buffer and a pointer to it using our sys.get our allocator. So allocator with uniform buffer allocator uniform buffer size. Oh, we didn't initialize an allocator. We should definitely do that. Let's do that after the context here. Allocator allocator dot with Vulkan allocator. Sorry, with allocator. And we need the physical device. We need the logical device. We need the instance. We need the API version, which we can just get from the config here. So we're going to need to do 2 things. Import the allocator and use overloaded record dot. That's because the API version function, like that's used to access the API version from the application info, is ambiguous. The Vulkan bindings are like automatically generated, so there's a lot of ambiguous functions. Best way I found to like get around that is to just use the record dot syntax, which I've never really used before, but I think it's familiar to people from other languages, coming from other languages. All right. So just doing a little bit of type massaging. Cool. So we've allocated our uniform buffer. We've got a pointer. we will need to poke some data into that pointer. So what we'll do is we'll get our uniform buffer pointer. We'll convert it from the current pointer type, which is unit, to pointer type of floating point matrices, 4x4, and then we've got to put in our data, and we're going to have to generate our data. So let's do that. Say let new uniform buffer data equal get uniform buffer data. So we're going to rotate this square, so we will use time to figure out how much to rotate it. We'll give it a start time, the current time, which we'll go ahead and get now. Lift IO Kronos.now. Import that. Start time, current time, and then we need the swap chain width and height. We'll be using that to calculate the projection matrix, I think. One of them, we'll see. Width. And the same thing for the height. We'll import this extent 2D type. Got to get it from a particular place. There we go. Alright, so let's define this now. I'll just copy this from my last project and we'll explain it. So first things first, we'll need some imports. Linear. Cool. And torso. Alright, so it's going to get the difference between the current time and the start time. Convert that to a float. And then use that to rotate we're doing some conversion here between like an angle and radians, or we're multiplying some radians by the time passed. And that's going to happen on the z-axis, which I think is straight up in this case. Or it's going to be straight up. We're creating a model matrix. In this case, the model is just going to be at 0, 0, 0. So at the origin. We're going to create a view matrix using this linear library. It's got a lookout matrix, so we can give it an eye position, where it's looking in an up direction, and then we're calculating a projection matrix using this perspective function. And we're making sure to transpose it and then set the multiply the y value by -1. Just because of the difference between this math library and Vulkan. Right, get uniform. So we've got the current time, but we don't have the start time. So before we start our loop, we'll just get the time. We'll call that our start time. All we want is just a fixed point that we can compare to. It doesn't matter where that fixed point is. So we've got our new uniform buffer data. We can just poke it in. So now we've written to our uniform buffer, but we haven't actually bound our uniform buffer to a descriptor set. And we definitely want to do that. So there's a couple of things we have to do. We have to let Vulkan know that this buffer is going to be bound to a descriptor set, and then we have to bind the descriptor set before we draw. So if I was to do that, let's vk update descriptor sets. So we've only got the one descriptor set, so we don't have to worry too much here. So the first argument here is going to be a list of writes. Second argument is going to be copies. In the copies, we're just going to leave that empty. So if we have a look at this call, so yes, we've got the device, a list of descriptor writes, and a list of descriptor copies. The write descriptor set is a fairly large structure. So we're not doing any copies, but we are going to do one write. And we'll just do our typical vk write descriptor set. First argument is that chain argument, which is always going to be null. We will just get our set. This is our destination binding. So the binding is 0. The array element is 0 because we aren't using an array. The count is 1. So we're binding one descriptor set to the destination binding 0 in our shader. The type is a descriptor type uniform buffer. And what's this one here? Image info is empty. I'll leave that as empty. What's the next one? Buffer info and texel buffer view. So we'll call this texel buffer view, and this one is going to be the one that we care about, which is buffer info. So vector.singleton vk descriptor buffer info uniform buffer. So we give it the uniform buffer, we give it an offset, and then we give it the size. Cool. So now we've told Vulkan that this descriptor set is going to use this buffer. Then all we have to do is right before we draw is bind that descriptor set. But we have a slight problem, which is that we extracted this kind of common pattern that we had where the frame data was recorded to. So if we look in render, we've got this function called record frame data. What that does is it takes our frame data, goes through each render pass, and begins the render pass, sets up the viewport, and then for each subpass, we're going to bind the wrap pipeline, make sure to bind the vertex buffers, do the draw call, and the render pass. So that's great, but right before, where we're binding the index buffers, we also need to bind a descriptor set. But I can't think of a super easy way of doing that right now. Just with the way that we need to, we don't have the right tools right now to easily distinguish between data that's needed for every swap chain image view, data that's needed for each frame in a flight, and data that's needed like once, data that's needed just for a frame. We don't really have a good way of distinguishing that. And I did try and put this binding descriptor sets in here, and it took me a long time and it wasn't that much fun. So what I'm going to do is, just for now, in the interest of getting things done, what I'll do is I'll spend some time thinking of a better way to do this later, is we'll just get rid of this function call here and go ahead and duplicate this code. Okay. So there we go here. And then we can just bind our descriptor sets here. We should have a look at this function. Command buffer, bind point, layout, first set, then the sets, and then offsets. So, what's that going to look like? Command buffer, VK pipeline, bind point, graphics. We'll get the pipeline layout. We'll have to find that. We'll leave that there for now. So the subpass. Let's have a look. It doesn't have the pipeline layout. So that's interesting. We'll come back to that. The first set to 0. And then the set that we're binding. That's pretty simple. Then dynamic offsets, which we just set to 0. Make sure to import what we need to import. And then let's see how this compiles. So not very. Got some things to import. So we're just importing those. Cool, so now we've just got this one issue with the pipeline layout. So what's happening is we're getting to this we've got this subpass, but the pipeline layout isn't specified here, so we can't really get it. So what I think we should do, let me just have a little think. Yeah, we can modify the um, subpass to have this pipeline layout in it. There's nothing wrong with that. And instead of the user creating the pipeline layout, we'll just get them to give us their descriptor set bindings. Then we can create the pipeline layout on their behalf. Cool. Can change this. Now we're going to have to fix render. Okay. So when we're creating the frame data, we're gonna have to modify this. Here we go. So before we do this, we're going to need to create the pipeline layout for the subpass. All right. What we'll do is we're going to output the subpasses from this block. So first thing we've got to do is create our pipeline layout. Subpass info. So instead of passing in the pipeline layout, we'll pass in our descriptors. Actually, we might not be able to do that. We'll ask them to pass in their descriptor set layout. So they won't create a pipeline layout. They'll just give us a set layout. Kind of flying by the seat of my pants here, so we'll see how this works out. Alright. So we'll create the pipeline layout. And we'll pass in set layouts from list, subpass info, descriptors from the subpass info. Great. So we've got an allocated pipeline layout. That'll get used when we create the pipeline. So pipeline create info. It's going to go through. Then we're going to create the pipeline. We're just going to create one at a time instead of creating them all at the same time. That might be an efficiency loss, but we'll deal with it. Probably indented this wrong. Yep. Gonna need two more spaces. Cool, we got a pipeline. And what we're gonna make is a subpass. So what we need to do is get our pipeline. What is a subpass? It's subpass, pipeline, pipeline layout, and then a drawer. And we can get rid of this whole thing. Cool, so we're just returning a subpass. We're turning all of our subpasses. But we've got to let's fix some errors first. Possible I gotta return this as a list maybe. No, I should be good there. Cool. Let's see what we're getting back from this. That doesn't look like what we want. So 4M. That'll do it. Yeah, that's fine. Yeah, we'll fix that. This is the important error. Okay, so we'll fmap sequence this to change it from a list of resources to a resource list. Great, that looks like that worked. Alright, so now we need to go to our examples and get rid of the pipeline layout. Subpass info pipeline layout. So instead that's now called descriptors. Let's call it, we'll just call it descriptors for now. And why doesn't that work? Yep, need to resource.get. Not do that there. Great. Now we just need to go to our triangle example, also get rid of the pipeline layout, also change this to descriptors, but we can just give it the empty set here. because we're not using any descriptors, and the same here in our buffer example. Cool, pipeline layout. Go ahead and destroy that. Cool, all right, well, maybe this works. So we are binding the descriptor set, and that's great. And we're updating the descriptor set, allocating. We'll give it a go. Oh, I cannot believe that worked the first time. All right, cool. Let's change this clear color because it's starting to annoy me. Render clear values. We don't have a way to specify clear values at the moment, so this is going to change all of our examples. Oh, but only if I reload it. Okay. What happened there? Ah, yes. We're not using the same code here. Great. That looks better. All right, but we did get a validation error. Let's have a look. Ah, it's invalid to call free descriptor sets with a pool created without setting descriptor pool create free descriptor set bit. Let's have a look. So there's this article called Writing an Efficient Vulkan Renderer by this guy named Arseny. I probably mispronounced that. But it's very useful. And I think he talks about this. Though I could be wrong. While it's possible to free individual descriptors from a pool, this complicates memory management on the driver side is not recommended. Okay, well, let's just not free then. Vulkan. So rather than freeing the descriptor sets, we will just allocate them. So with VK descriptor set. Yeah, that should be fine for now. So VK allocate descriptor sets device, and we've got our allocation info. Oh wait, that's the wrong one. Here we go. VK allocate descriptor sets device, and then we've got our allocation info. So we're not going to free this ever, but when the pool is destroyed, this will automatically be freed. And that's the recommended way to do it anyway. Not recommended to free descriptor sets, just free pool. So we don't set up so anywhere we're using resource.getSet, is going to be a problem. Yep. Allocate descriptor sets. Ah, yes. It's going to take a third argument, which is nothing. And so what have we got here? Just going to fix these errors. Allocate descriptor sets. Alright, so we don't actually need this. It's giving me an IO, so we can just fmap vector.head. That should work out, but it's not. Why is this a resource T? Let's try this again. Definitely missing something here. Just call this function. And we'll just say, let's set equal undefined so we can silence any errors about that. Couldn't match vector descriptor set. What? Allocate descriptor set. Oh, there is no allocation callback. Ugh, that's annoying. Alright. Cool. Back to working. Okay, so we've just got our uniform buffers working. We're creating a new uniform buffer every frame, but the Vulkan memory allocator is handling that for us. So it's making that efficient. It's allocating like a big allocation and then giving us a little piece of that without actually having to allocate any memory. And we can just confirm that it's still the case by having a look at the pointer that's returned. So you can see that the address of the pointer isn't changing, even as we go across frames, because we're freeing the previous allocation before we start the next frame. So that's cool, because like, yeah, we're like allocating every frame, but we're only using like enough data to hold this this set of matrices. So we have kind of, let's commit this first. Let's do that first. Call this. Let's call this working uniform example. Right, so push these commits up. So yeah, we can follow these commits live at github.com/sambennett/RORT, sambnt/rort. Cool, that's up. So we've kind of made a compromise here. In our first two examples, the triangle and the buffers, so the vertex buffers, we were able to extract out some common code, and we put that in this like module renderer. Because like one of the things that we wanted to do when designing this program is use raw Vulkan as much as possible and then extract common patterns when we find them. And we did find some, which is like, we just kind of specify what the render passes will look like. And then from that, we can derive frame data. And frame data is essentially data that needs to exist for every swap chain image view. And then we found that, okay, well, given that frame data, we can actually record our draw calls. So we like iterate through the render passes, we start a render pass, set up the viewport. Then for each subpass, we bind the pipeline for that subpass, bind the vertices, bind the indices, make a draw call. What would make sense for us to do is to put something in here that's like, okay, and now bind descriptor sets. But what I found was that didn't quite work. And the reason for that is there's a few things going on. What we need is we need to be a little bit clearer about the lifetime of resources. So like Vulkan, it just seems like the whole time we're just managing resources. Um, some resources, like our render passes, they need to be created for every swap chain image view. It's like replicate, or like the render pass can stay the same, but um, we'll have like one set of render passes, but then we'll need to create a frame buffer for every swap chain image view. Um, and then we've got frame in flight. So we might have like double buffering or triple buffering going on. And then we have 2 or 3 frames in flight. And then we've got resources that we need for each frame in flight. So in our case, descriptor pools are needed for each frame in flight. And also like semaphores and fences that we use for syncing, they're required for each frame in flight, but they're not required for each swap chain image view. So you can kind of see we have this like kind of like different multiplicities, where we have some resources that just need to be created once, some resources that need to be duplicated for each swap chain image view, some resources that need to be duplicated for each frame in flight, and then some resources that need to like be created each frame and then live just for that frame. And we're not really capturing any of that in what we have here in our renderer. So I think what we need to do is have a little bit of a think about how we might start to take the description of the render passes that the user gives us and sort of split it into data, split that information up and create the things that we need at the multiplicity that we need. Yeah. So I think like this is what kind of motivates the renderer. So like we'll create maybe like a data type and start, yeah, filling it out. We'll take the render pass info that the user gives us and start filling out that data. And then hopefully we can arrive at something where instead of just having like one descriptor pool and a single threaded and assuming a single threaded environment, we can assume like a multi-threaded environment and make sure that descriptor pools aren't being used across threads and all that kind of stuff. Um, so yeah, so we will get onto that. I think I'll take a little break before the final hour of the stream, and I'll be back soonish. So thanks everyone for watching and your patience. Like I said, this stream we're a little bit less prepared, but hopefully that's good. Hopefully we can discover some things together. All right, be right back. All right, we're back. So, anyone just joining, what we've done is we've made our uniform example work, which is just rendering a square, and we are transforming the square using like a model view projection matrix. Uh, and we've got a kind of frame-based allocator that allocates very simple, allocates well, our choice of technologies has made it very simple. That just allocates some memory for that particular frame. So we can allocate enough memory to hold three matrices for the frame, no problem at all. And now we've kind of identified that the abstractions that we have, and we don't really have abstractions, we've kind of just taken out some repeated code and put it into some functions. They're not really serving us. We're not able to express what we needed to in order to render this uniform buffer example. We sort of had to cheat. So what we're going to do is have a little think about, brainstorm how we might change that so that it makes more sense. So at the moment, this is kind of our only abstraction, really. I mean, we've got a bit of abstraction around the swap chain, bit of abstraction around resource management, but mostly we've just got this function, this module called render, that's got two functions in it: make frame data and record frame data. But we've identified that we have kind of three lifetimes or four lifetimes even. We've got things that are created initially and then aren't expected to change. We've got things that need to be recreated or need to have a copy of for each swap chain image view, uh, like frame buffers, for example. We've got resources that need to be created for each frame in flight. So if we're double buffering or triple buffering, um, we'll have resources that need to exist for that frame. And then we have like per frame sort of resources. So resources just exist for the time that the frame is rendering, no matter what frame it is. So if we have a look at our swap chain, we have this thing called swap chain frames. And this is actually like probably one of the only thread safe parts of our renderer. Um, Using this, we can call this function called with next frame in flight, and it'll give us some synchronization primitives that we can use to present an image to the screen and make sure that the previous image has finished rendering and stuff. So this is like a kind of a base synchronization for rendering to multiple images and making sure that we are rendering to an image that isn't currently presenting, etc. But I'm thinking that this doesn't actually belong in the swap chain. So let's have a look. How is this used? Um, yeah, yeah, it's not really used. Wow, this num frame is in flight. How is this used? Yep, it's not used. So these two things are kind of independent of the swap chain. How many frames we decide to render to at the same time is independent of the swap chain and how many image views are in the swap chain. So let's extract this. Let's take this out. Um, we'll move this data type to the render. Let's create a renderer. And we'll move this code from the swap chain to the renderer. Make sure to import. Okay, great. All right, and then we can take this with next frame in flight function, and instead of it operating on swap chain, it operates on the renderer, which makes a lot more sense. Need to import what we need to import. IO.class, and it's going to be renderer frames. Okay. We'll keep going. So does the swap chain need the num frames in flight anymore? I don't think it does. Cool, so we can remove that parameter from the swap chain, but we are going to need it in the renderer. Okay. And we can remove this stuff about the frame queue and put it in the renderer. So we don't need this anymore. So this was to recreate the list of frames whenever the swap chain changed, but we don't need to do that anymore. This stuff is all independent of the swap chain. So for the number of frames in flight, we're going to create one of these frame sync structures. Then we'll write them to the queue, and that'll be our initial queue, frames queue. And the renderer will just be made up of the frames queue and the number of frames in flight. Cool, so let's get rid of what we can get rid of here in the swap chain. Let's move this frame sync. Move this frame sync stuff to the renderer. And move this vent stuff. Move that to Vulkan, where we've got all of our other resource related things. So we'll just make this fit the pattern of the other resources using our resource type, which I need to note. We should revisit that. Because there's another thing called acquire that we might be able to use. But anyway, it'll do for now. So we'll change these to match the types that already exist in that module and do the same here. We'll import them. And because these are resources, we'll need to get them. Okay, great. STM, replicate M needs to be imported. We need the device. Okay. All right, so that should be good. So let's give this a type signature. I mean, we haven't done much, but we have started to kind of identify one area of independence. Um, so what should we call this? Because we've got the frame sync, but I imagine that we actually want to represent all of the things that, um, let's call this frames in flight. Yeah, I imagine we're going to add other data that is sort of that needs to be replicated for each frame in flight. Hmm. The interesting thing is that, well, the complicating factor here is that um, another part of this is just that when the resource is created or when we have the information required to create the resource. So when we first create the renderer, the only information we have is the number of frames in flight. We don't actually have any information about like the render passes, and possibly we can pass them in, but I don't know how I feel about that. Let's just leave this as just leave that as it is. We'll get back to that question. All right, well, we are going to need to create this renderer. It's probably right after allocator, say with renderer. EK device, context, and the number of frames in flight. We've got that somewhere here. Great, so now I've got a renderer. Let's see what the compiler says. Things are no longer available from there. And they're going to need to be imported. So we're going to pass the renderer instead. Let's fix these errors. We've got, yep, don't need number frames in flight. Semaphore. All these semaphores need to be imported. Cool. That's good. Yep. And then we need to do the same for buffer and uniform, but let's leave that for now. Buffer and triangle are previous examples. Leave that for now, just in case we change things like a few times. We don't want to be constantly updating our previous examples. Okay. So we are able to specify a lot up front. We're able to specify the shaders, the pipeline, descriptor set layout, uh, yeah, like kind of our vertex input structure here in the subpass info. You can see, yeah, specifying the vertex input structure and even the draw call. But to what we can't do up front is, at the moment at least, is allocate a descriptor set from the pool, write the uniform or like attach the uniform buffer to the descriptor set, um, and then bind that descriptor set. We can't figure that all out up front. Or maybe we can. It would be even nice to change, like, none of this changes, like the vertex bindings and the vertex attributes, they're not going to change once they're created. But what will change are like the draw calls. Like this is more of a dynamic structure. Um, you might have the same shader, but you might draw something different every frame. So it doesn't make sense to specify this stuff like right up front. So why do we do that? Let's have a look at that. Because yeah, if we can figure out this dynamic part, we can probably figure out the uniform buffer dynamic part too. That's my reasoning. So when we get to recording the frame, we do need to know the draw call, but we don't actually need to know it up front here. I'm pretty sure the only reason I'm making it so that you have to pass this in up front is because I don't have any way of associating a particular draw call with a particular like subpass. Um, okay, so let's imagine we have like another TQ. We could even pass in the extra information here. When you want to acquire the next frame in flight, you have to pass in the render pass info or the something. Maybe we'll get back to that. What would that look like? Data per frame in flight. So we need a descriptor pool per frame in flight because they can't be shared across threads. Like multiple threads can't use the same descriptor pool. And at the moment we're only going to have one thread per frame. Although we could multiply this by like the number of threads. So everything in this structure is going to be multiplied by the number of frames, and then we further multiply it by the number of threads. But let's just start with one for now. So we've got a descriptor pool for that frame. Do we need a command pool? Let's have a look. Pretty sure command pools are the same. They can't be shared. cross threads. Mm. Command buffers allocated from one pool may not be recorded concurrently by multiple threads. Here we go, yeah, F times T. F is the frame queue length. T is the number of threads that can concurrently record commands. So we're just going to assume that T is always 1. As in, like, every time we acquire a next frame in flight, this block is going to be single-threaded. So we can multi-thread this frame in flight, so we can be rendering 2 frames at once, just that each frame is only being rendered by 1 thread. And we'll relax that restriction in future if we want to, but there's no need. No need right now. What's going on here? Okay, descriptor pool, command pool. Then I would start my frame, and I'm going to get kind of my per frame in flight data. So I'm going to get my frame sync primitives, but I'm also going to get descriptor pool, command pool. So let's just imagine what that would look like. So I got my next frame in flight, got a descriptor pool and a command pool. So rather than me creating one here and here, that'll be created for us. But in order to create the descriptor pool, I need to know how many, like, uniform, like, what the size of the pool should be. And I can get that from the render pass info. So the renderer at some point is going to need this render pass info. Which is fine. Might even just pass it in here. Oh yeah. And do we need anything special for the command pool? No. Okay. Never mind. Now things like the set layouts and stuff like that. Because the thing is that we need to be able to refer to the set layout in order to allocate the descriptor set. So that set layout needs to make its way into the subpass. So that when we're iterating through the subpasses, we allocate a descriptor set using the set layout in the subpass. Let's just quickly have a look at the types. Yep. We use the descriptor set layout in the subpass to allocate a descriptor set or multiple of them. That's cool. We would have got the descriptor pool from the frame in flight, and then when we're drawing, well, that will happen when we're drawing, we need to obviously allocate our buffer, but that's fine. We need to update the descriptor set. So we need to know what the descriptor set is. So maybe what we'll do is we'll give the user, as we go through these render passes, Like we'll do all the setup for the render passes and stuff, but rather than, binding these vertex buffers and making this draw call on their behalf, we'll just like let them do it. So we'll just like open this up, this basically this block here, where we're binding dynamic resources. We'll just let the user do that. And that way we don't have to, we'll give them all the things they need, like a descriptor pool and a command pool and whatever. I think that makes sense. So rather than record frame data being just something that we call, it'll be something that we call and give an argument that's a function that it will call on our behalf to draw the frame. All right, I'm going to write that down. So bind vertex, bind index, bind descriptor sets, and actually make the draw call. All right, well, we'll give that a go and we'll see how it goes. Wow, everyone joining my stream right at the last minute. All right, so what we've done today is we have got our uniform buffer example working, but we just identified that there are a few issues around the way that we are creating resources in their lifetimes, kind of hacked it to get this to work. So we thought a little bit more about the various lifetimes of resources, whether that's like they exist for a long time, they need to be duplicated for every swatch chain image view, or they need to be duplicated for every frame in flight, or that they are created and they only live for a particular frame. And so we're going to start to identify those different types of resources, put them in different places, so that we can start to create a renderer where those lifetimes are a bit more clear, and we've got kind of the multiplicity of our resources makes sense. But we're getting towards the end of the stream, so I think we'll finish a little bit early because, like I've said, for the last hour or so, we've been kind of off plan. So yeah, I'll probably spend the weekend taking a look at this idea, see if we can get a better structure for our code, and we'll go through that on the next stream. So you can follow all of these commits live at github.com/sambnt/rort or rort. So you can get the commits here, and then all of these streams are uploaded to @SamBennett_TV at YouTube. So you can see previous streams. So thanks so much for joining me today, and I'll see you next week. Stream schedule will be up soon. It'll be a little bit different this week. I'm just experimenting with stream times. So yeah, great to have you and have a good weekend. See you everyone.